Okay, so today we'll finish the classification of surfaces. Last time we were in the middle of, or really at the end of proving the abundance theorem. So let's recall the theorem. Let X be a minimal model. In dimension 2, meaning a smooth projective surface with Kx and F. Then Kx is semi-ample. And the proof of this, we went through all the different cases with the possible Kodaira dimensions and had to do different things in each case. And at this point, we were on the last case, which was the case of Kodaira dimension 0. The genus is 1, and the irregularity was 2. Okay, and then in this case, the Euler characteristic was 0. And what we had shown so far, well, we took the Albanese map. Where what's A is some two-dimensional abelian variety because the irregularity is 2. And we had shown that alpha is surjective. And since X is also two-dimensional, then this means that it's in particular it's generically finite. And we did this by saying suppose it factors through some curve, then this A is the Jacobian of that curve, and that curve is necessarily genus 2, but then genus 2 curves have high genus étale covers, so we can base change. And when we base change, we get some surface that's Kodaira dimension 0, but has the wrong numerical conditions that just can't exist. So it can't factor through a curve. So we did that last time. And now we want to conclude from this that alpha is actually étale. That's our goal. So it's actually some finite unramified cover. Okay, so let's look at Riemann-Hurwitz for a second. So what does it tell us? It tells us that the canonical of X is the pullback of the canonical downstairs plus some ramification divisor, which I'll call E. And the key point is that E is effective. And this is essentially because on the locus where the map's unramified, then the canonical just pulls back to the canonical because you just check on differential forms. Because when it's unramified, it's a local isomorphism. And so you know there's going to be a formula of the form Kx equals the pullback plus some correction term, where the correction term is supported exactly where alpha is not unramified. And then to check that it's effective, you see that any pullback of differential forms extend. Okay, and now we know what the canonical of A is. A is an abelian variety, so we know that means that the canonical of A is actually trivial. So really, we know that the canonical of X is exactly this E, which is this ramification divisor. Okay, on the other hand, we also know that kx squared is 0 because we're in the Kodaira dimension 0 case, and x is and k is minimal. Sorry, k is an f, and so kx squared is the same as e squared, so e squared is also 0. But now this implies, by the Hodge index theorem, that there's some component d contained in E, let's say an irreducible curve, such that alpha of d is not a point. So there has to be some component in our divisor E that's not contracted by alpha. And the reason for this is because if all of E is contracted, then by Hodge index theorem, we have these divisors that are exceptionals of a map to something, of a finite map to something two-dimensional. And so by Hodge index theorem, we would have that E squared is strictly less than 0. That was one of the things we mentioned in the maybe second class, one of the corollaries of the Hodge index theorem. So because we know E squared is 0, there has to be at least one component that's not contracted to a point. On the other hand, let's look at what this component must be. So let's just write some notation. Let me call this component D0. And then E will be some N0 D0 plus whatever other components there might be. Sorry, and here I should have said if E is not empty. It's possible that E is just empty, and then we're done. So here we'll say if E is not just the 0 divisor, then it contains such a component. It's possible that E is actually just empty, and that's actually what we're trying to prove. We're trying to prove that E is empty, in which case alpha has to be unramified. Okay. Are there any questions? Okay. So we have this E, and now let's just compute. So 0 is kx squared, which is equal to kx dot E, since kx is equal to E according to our formula. And now this is greater than or equal to kx dot n0 d0, and this is because kx is an f. So all the contributions from kx dot these other di's are all non-negative. So when we subtract those, we get something smaller, and then now we again use that kx is just E, so this is E dot n0 d0, and now this is greater than or equal to n0 squared d0 squared, because these di's are different divisors from d0. So d0 is one irreducible component, and then the di's are some other irreducible components. So they have to intersect d0 non-negatively. So when we subtract those off, we again get something that's smaller. So putting that together, we get that, and then of course n0 here is at least 1. So we get that d0 squared is less than or equal to 0. Okay, but now by adjunction, kx plus d0 dot d0, well, kx dot d0 right. Kx dot d0 here is less than or equal to 0, but because kx is nef, that actually means it has to be equal to 0. So here we see that kx dot n0 d0 is less than or equal to 0, but also it has to be greater than or equal to 0 because d0 is effective, so it's actually just 0. So kx dot d0 is 0, and then d0 squared is less than or equal to 0, so this whole thing is less than or equal to 0. But this is the degree of the canonical of d0. So d0 is some curve whose canonical has degree less than or equal to 0. So d0 is either rational or elliptic. Okay, so we found some curve that's sitting inside of the ramification divisor of our Albanese map, and that's not contracted to a point by the Albanese, and it has low genus. But by the functoriality of the Albanese, we know that if D is P1, or if D is rational, then the composition of the inclusion of d0 into x and the Albanese of x must factor through the Albanese of d0, which is just the Jacobian. But the Jacobian of a rational curve is just a point. But we showed above, where we picked d0 above so that it was not contracted to a point. So it actually has to be an elliptic curve. Okay, so this is impossible. So d0 is an elliptic curve. Okay, and now we have to use some geometry about abelian varieties. So it turns out to be the case that for maps between abelian varieties, up to translation, they're group homomorphisms, because abelian varieties have this group structure. So if we look at x mapping to the Albanese by alpha, up to translation by some element of A, we can assume that the image of this d0, which is also some curve, is an abelian subvariety, meaning that it's actually a subgroup in the group structure. And so then we can compose by the quotient by the subgroup, which is some other elliptic curve. So we're taking a two-dimensional abelian variety and quotienting out by some one-dimensional abelian variety inside of it. And so now we can look at this composition. It's called beta. And what do we know about beta? We know that D0 is contained inside of a fiber of beta. Specifically, it's in the fiber over the origin of this abelian variety. But D0 squared is 0. So again, by the Hodge index theorem, this is a different corollary of the Hodge index theorem. If we have something contained in a fiber whose square is 0, then it has to actually be a multiple of the fiber. So this implies that MD0 is beta inverse of 0 for some number m. So we have this, we found this D0 that's contained inside of Kx, where Kx is some effective divisor. And we know that this D0 is up to multiple the fiber of a map to a curve, of a map to this elliptic curve A mod alpha of D0. So now we can compute Kodaira dimensions. So the Kodaira dimension of X, by definition, is this growth rate for the space of sections of the canonical, this Itaka dimension of the canonical. The canonical is some effective divisor which contains D0. So this has at least as many sections as D0, because it's D0 plus some more stuff. But then D0 is this fiber of a map to a curve, so this has to have Itaka dimension 1, because D0 is the fiber of a map to a curve. So this contradicts our original assumption that the Kodaira dimension of X was 0, that we were in this last Kodaira dimension 0 case. So that tells us that E has to be empty. So this map alpha is unramified, and the pullback of the canonical of A is just the canonical of X. But we already said the canonical of A is 0, so that tells us that the canonical of X is 0. In particular, it's base point free, and it really is just a 0 divisor. So that proves abundance in this case, that this Kx really is the 0 divisor. But it actually proves a little more because we have this map to an abelian variety that's unramified. And if you think about the geometry of abelian varieties, there are these quotients of vector spaces by lattices. And these finite unramified covers will correspond to covering spaces in topology. And the only covering spaces of these tori are also tori. And so whatever X is, it itself has to be an abelian variety as well, because it's some finite covering space of an abelian variety. And that's why we called this case, where a priori we just said that a surface with these numerical conditions is called an abelian surface, and here we see that it's actually a two-dimensional abelian variety, and that's why we gave it that name. Okay, so that's the end of the proof of abundance. Okay, so now we're basically done with the classification, modulo a few steps of actually understanding what these different surfaces look like. So let's write down the full classification. But like I said, most of this will be a summary. So let's make a table with the Kodaira dimension, the irregularity, and the genus. And then over here, we'll write what the minimal model looks like, or what the minimal, a minimal surface that we get after blowing down all -1 curves looks like. So in codary dimension -infinity, if we have irregularity 0 and genus 0, then we have the minimal model is a minimal model is P2, or a minimal surface. I shouldn't call it a minimal model. So something with codary dimension -infinity, irregularity 0, and genus 0 is a rational surface, so it's birational to P2. So it's possible that when we contract -1 curves, we end up with P1 cross P1 or some ruled surface over P1, but they're all birational to P2. So we can put P2 as our minimal representative. That's a minimal surface. Still in codary dimension -infinity, if the irregularity is strictly greater than 0 and the genus is still 0, then we end up with a ruled surface over a curve of higher genus, where specifically the genus is the irregularity. And in particular, if we just want one representative, the same way how in the rational case we can just pick P2 as our birational representative, here we can just pick P1 cross C as our birational representative, since all ruled surfaces over the same curve are birational. Then in codary dimension 0, with irregularity 0 and genus 1, here we have K3 surfaces, where we showed that the canonical is trivial. And you can take this as the definition of K3 surfaces. They're the surfaces in this part of the classification. Then we have in codary dimension 0, but with irregularity 0 and genus 0, we have these Enrique surfaces. With 2kx trivial. And what we'll show is that these are quotients of K3 surfaces by involutions. So an Enrique surface is always of the form K3 modulo an involution that acts freely. So that's one of the things left to prove in this theorem. So far, everything else we've already proved. This is the first thing left to prove. Then we have abelian surfaces, so just two-dimensional abelian varieties, which have codary dimension 0, irregularity 2, genus 1. And here again, the canonical itself is trivial. We have bielliptic surfaces, which we still have to justify the name bielliptic. So they have codary dimension 0, irregularity 1, and genus 0. And these satisfy that mkx is trivial for some m greater than 1. And we'll show a little bit more that actually they're of the form product of elliptic curves modulo some group action. So modulo some finite subgroup of the automorphism group, and this m is exactly the order. Maybe I'll just write G, where this m is the order of G. And that's why they're called bielliptic, because they're quotients of products of elliptic curves. Okay, and then in codary dimension 1, the irregularity can be anything non-negative, and similarly for the genus. And these are all elliptic surfaces. So we'll see that they're all genus 1 fibrations over a curve. And I'll say more precisely when we prove the theorem, how we can determine their structure. And then finally, in the last case, Cordaro dimension 2, by definition, we get surfaces of general type. And on our minimal model, we have the property that Kx is big enough. And we can characterize these as being resolutions of singularities of what are called canonical models, which I'll define when we get to this part of the proof of this theorem. But the defining feature of these canonical models is that the canonical divisor of the canonical model is actually ample. So basically, the idea is you can understand these surfaces of general type by understanding the surfaces whose canonical is ample, and then these can be singular, and then we resolve their singularities, and that's how we get these minimal surfaces of general type. Let me flip this around so we can see the full table at once. Okay, so that's the full classification of surfaces, and let me star the things that we still have to do. So for a circle, we have to prove this. We have to prove this. And then we have to kind of justify these claims here. And actually, let me just number these for the proof. So things that we have left to do, we'll call this case of Enrique surfaces A, the bielliptic case B, the elliptic surface case C, and the surface of general type case D. Okay. So for A plus B, we're going to use a certain construction that will come up a lot later in the class as well. Here we'll just use a special case, but it's a very useful construction. So what do we know in these Enrique's and these bielliptic cases so far? What we know is that n times the canonical is trivial for some m that's strictly bigger than 1. So another way to phrase this is that there exists some f in the line bundle OX of MKX such that f has no zeros or poles. So maybe I'll write it as f is a global section, so it has no poles, but also it's non-vanishing. That's an equivalent way to say that MKX is the trivial divisor. It has some non-vanishing section. And so using this non-vanishing section, we'll construct what's called the cyclic cover. And the cyclic cover trick is quite powerful. So the cyclic cover, kind of the cartoon picture is that you're taking y to the m equals f. So you're taking the vanishing locus of the equation y to the m equals f, calling it x tilde. This projects down to x, And what is this doing? On this x tilde, we have an mth root of f. And because f is non-vanishing, taking the mth root should be well behaved. And so what does it mean to take an mth root of f? Well, exactly what it means is that upstairs on this x tilde, where before we had m times the canonical was trivial, on x tilde we should just have that the canonical itself is trivial, because we found a trivializing section, specifically the mth root of f. Like on x, the reason it's not trivial is because this f doesn't have an mth root, so let's just build some cover where it has an mth root. That's the idea. So and so one way to actually carry this out is to find charts on X. So cover X by some open affines, where this, just cover X by open affines, and then you can make sense of y to the m equals f just in the coordinates of each of these open affines, and then glue them all together to get your x tilde. But another way to do it is to use the relative spec construction. So let me write down that. And of course, in the definition of relative spec, if you write down the definition, you'll exactly get this construction using affines, because how relative spec is defined is exactly by taking an affine cover, taking actual spec on each affine cover and gluing. So it ends up being the same thing, it's just maybe a more compact way to present it. So here's the more precise definition of x tilde. We take relative spec over x of the following sheaf of algebras. So we take sums of OX of minus multiples of the canonical up to minus m minus 1. So m is the place where the canonical becomes trivial, and we take minus up to the place right before it becomes trivial. And so to make sense of the spec, I have to define what the algebra structure is. It's going to be a graded algebra. So let's call this whole thing A. It's going to be a graded algebra because I presented it as a direct sum. And how do I define maps from A tensor A to A, this multiplication map? Well, I need to define them on each summand separately. So I need to define maps OX of minus A KX tensor OX minus B KX to where's the product going to land? Well, normally, if I take tensors of sections of bundles, I get to the sum. So normally I'd get minus A plus B KX, but that's not going to be something in our algebra because our algebra cuts off kind of at this mth step. And so where we want to land, we want to actually shift everything down by m to land here so that minus A plus B minus M is actually one of the summands in our algebra A. And how do we do this? Well, we use our F. We use that we're given a specific F that's a section of O of M KX. So F here is a section of M KX. And so we use that to give this shift. Because when we distribute this minus, we really have plus M here. So the definition is just that you take S, which is a section of minus A, you take T, which is a section of minus T, of minus B, and then you map it to the product ST, which is a section of minus A minus B times F, which shifts it back up by M. And so using this F, we get an algebra structure on this A, a graded algebra structure, and then we can define this relative spec. It's going to be some finite cover of X, and it's going to be degree M. So this X tilde to X, basically by definition, is a degree M cyclic cover Cyclic here means that the cyclic group on M elements acts on X tilde, and it acts kind of by the grading here. So an action of mu m of the cyclic group of M elements is the same as your algebra that you're taking spec of being graded by the elements of the dual group, I guess. But basically, because we're taking spec of a graded algebra with m pieces, that's the same as saying that whatever our spec is has an action of the cyclic group of order m. And so this beta is a cyclic cover, and its quotient x. So and then the other point is that x is the quotient of X tilde by whatever this cyclic group is that acts according to these graded pieces. So that's what we get from the cyclic cover construction, and then we can compute. So we can now compute that kx tilde is beta upper star of kx, but it's actually just ox tilde using this trivialization, the mth root of f. And we also can compute that the push forward of ox tilde is exactly this algebra A, because that's how spec works. Or more explicitly, the direct sum of ox minus a kx from a equals 0 to m minus 1. Okay, any questions about that construction? So we're going to see a generalization of this construction soon, where one, we allow other line bundles, not just the canonical. I guess that one's maybe pretty clear what you do. You just put L inverse instead of minus K everywhere. But also where the section that we pick is not actually non-vanishing, and then we're going to have some cover that's not. It's not just a. It's not unramified, right? I should have said here. This is saying that beta is unramified. And more generally, we can construct ramified covers where we do a similar thing, but where our section actually has zeros, and then we'll get some ramification. And we're also going to need to do this in the case where x itself is singular, and then we'll need to control the singularities on X tilde, which a priori could be better or worse. Okay, so now we're going to apply this construction to our Enriques and bielliptic surfaces. So let's compute the invariance of X tilde. So because X tilde is unramified over X, the Kodaira dimension is the same. So it's still 0. And because of this formula that the canonical on X tilde is actually just a trivial line bundle or trivial divisor, then the genus of X tilde is 1, because that's how many sections the trivial divisor has. So the last question is, what's the irregularity of X tilde? And that we can compute in terms of this push forward of OX tilde. So by definition, this is H1 X tilde OX tilde. And then because beta is finite, this tells us that these higher direct images of beta are 0. And so if we want to compute cohomology upstairs, we can just push forward and compute cohomology downstairs. So this is the same as H1 on X of the push forward, which we have a formula for here. It's this direct sum of these twists by minus multiples of the canonical. So this is the same as the direct sum from A equals 0 to m minus 1. And here I should have put lowercase h's, since this is a dimension, of H1 on X of OX minus A KX from A equals 0 to m minus 1. And so now what's the idea? We're going to compute what Q is in the two different cases, in the Henry case and the bielliptic case, and then that'll tell us what X tilde is, because we've already, like, we have these other cases of K3 and abelian surface, which are the cases where the canonical is actually trivial. So we know that X tilde has to be one of these two cases. It has to either be a K3 surface or an abelian surface, depending on what the irregularity is. And then that'll let us get these statements that an Enrique surface is always a K3 modulo an involution, and that a bielliptic surface is a product of elliptic curves modulo some cyclic group. Okay. Questions? Okay, so let's check the two different cases. So in case A, what do we know? We know that M is 2, first of all, because we're in this Enrique's case. So in the Enrique's case, we already showed that 2 times kx is trivial. So in this direct sum, we just have, and I guess here, because I'm computing numbers, I should have put a regular sum, not a direct sum. Here we just have the a equals 0 term, and then the a equals 1 term. So we have h1x ox plus h1x ox minus kx. Those are the only terms that appear. This is the irregularity of x tilde. But in the Enrique surface case, if we go back up to our table, the irregularity of an Enrique surface is 0. So this term is 0. So now we want to compute h1x ox minus kx. Okay, so that tells us that this x tilde is a K3 surface, but we also know that M is 2, so we know that this cyclic cover is a Z-mod 2 cover. So it's the action is by some involution, and so that tells us that X is X tilde modulo some tau, which is an involution, where X tilde is a K3. Okay, so that's the Enrique's case. Then we have the bielliptic case. So here, what do we want to show? Okay, so again, we want to compute the irregularity. And we know that it's greater than or equal to the irregularity of x, because that's one of the terms in this sum, plus all these other h1s, but I'm just going to go to the first h1 that I know I can compute, and that's this last one, this h1 x ox minus m minus 1 kx, where m is this index, this number that makes k trivial. It might be even bigger, but I know I can compute this one. And I guess, yeah, Serre duality actually is easier here, so thank you for that comment. So by Serre duality, this is the same as h1 x ox of canonical minus negative m minus 1, so it's plus, so we just get mkx. But mkx is O, so this is the same as h1x ox, which is the irregularity, which we know is 1. That was one of our numerical conditions for the bielliptic case. So this is also 1. So that tells us that the irregularity of x tilde is greater than or equal to 2. But now going back to our options, that means we have to be an abelian surface, and the irregularity has to be exactly 2 once we know it's greater than or equal to 2. So in particular, we also get for free that all those intermediate H1s have to vanish. Okay, so by our classification, since kx itself is 0, then qx is 2, and x tilde is an abelian surface. Okay, but then we're not totally done. Now we want to show that this x tilde is actually just a product of elliptic curves. Or maybe we want to show that x tilde is the quotient of a product of elliptic curves, maybe more generally. Because right now we know that x is the quotient of x tilde. We want to show that x is the quotient of a product of elliptic curves. And so here we use the fact that the irregularity of x itself is 1. So if we look at the Albanese map of x, then this is some elliptic curve. Because x has irregularity 1. And now we know that x is a quotient of x tilde by some free group action. And if we look at this composition, we get some non-trivial surjective map from an abelian surface x tilde to an elliptic curve E. And now there's this Poincare complete reducibility theorem. Which basically says that up to taking unramified covers, every surjective map between abelian varieties splits. So maybe x tilde itself doesn't split. X tilde itself is not the product of E and some other elliptic curve, but we know that there exists some product of elliptic curves and some cover like this that kind of splits this surjection up to some unramified cover. So maybe the correct word here is it splits up to isogeny. So okay, and then we're done because we know that x is a quotient of x tilde, and x tilde is the quotient of some product of elliptic curves. So x itself is the quotient of a product of elliptic curves. Okay. Any questions? Oh, I guess it's not the end of the proof. That was just the end of the Kodaira dimension 0 case. Okay, so now we've classified all surfaces of negative Kodaira dimension and all surfaces of Kodaira dimension 0, or all minimal surfaces. So next, we have Kodaira dimension 1. So let's say that x is a minimal surface of Kodaira dimension 1. Then we proved during abundance that some large multiple of the canonical linear series for x is base point free. And because the Kodaira dimension is 1, this has to be a curve. And it has to be smooth by Stein factorization or by taking D large enough. So we have this map, and again, by taking D large enough or taking the sign factorization, we can assume that it has connected fibers. And now we can just compute. Let's say F is a fiber. let's say F is a smooth fiber. We know that the generic fiber will be smooth. So let's say F is a smooth fiber. Then F squared is 0 because we're a fiber. And also Kx dot F is 0 because this phi is a pluricanonical series. So by this like base point freeness property. So the canonical of F is also 0. So F has to be an elliptic curve. And so this phi is an elliptic fibration. Which we can take as the definition to be a surjective map to a smooth curve with connected fibers where the smooth fibers have genus 0, or genus 1, sorry. The smooth fibers of genus 1. And if we go back to the first class where we were talking about kind of the expected results of the minimal model program, this is the expected result in intermediate Kodaira dimension, that we get a fibration onto something lower dimensional whose fibers are k-trivial varieties. So in this case, the lower dimensional thing is a curve, and the fibers being k-trivial are exactly saying that they're elliptic curves. Okay, but then we would like to actually classify what these k-trivial fibrations look like. So for that, let me just give a summary of what elliptic surfaces look like. So the first step to classify this, we know what the smooth fibers are, they're elliptic curves. We need to know what the singular fibers are as well. So the first step in classifying these elliptic fibrations is to classify the singular fibers. And this is a famous classification due to Kodaira. Well, first let me start with the smooth one. So, okay, we can have a smooth fiber, which in Kodaira's notation is called I0. We can have a fiber that's like a nodal cubic, so it looks like that. It's called an I1 fiber. We could have a fiber that is a loop of P1s. So each of these are P1s with self-intersection -2. And depending on how many of them there are, we'll call this an IM fiber, where M is the number of P1s that appear in this loop. And then there's a few more singular ones, but still reduced. So you can have a cusp, like y squared equals x cubed. And this we can call a 2 fiber. We can have 2 P1s that are tangent, like this. So again, in these pictures, anytime you have multiple components, so in this case with the IM fiber, and in this case with the type 3 fiber and the type 4 fiber that I'm about to write down, c squared is always -2 for each component. So they're always rational and their square is -2. The last one looks like 3 P1s meeting where each one meets mutually transversely through a single point, but the whole thing is not transverse because we still have 3 tangent directions on a surface. And then we have some more complicated ones, which are non-reduced. These are called, so there's IN star, 2 star, 3 star, and 4 star. And there's some reason for calling these the star versions of these, but it's not so clear. And these, instead of drawing the full pictures, I'll draw the dual graph of the configuration, or I'll name the dual graph of the configuration of curves. So again, in all these cases, each of the curves are P1s, and they all have self-intersection -2, and the graph in their that describes the configuration are these Dynkin diagrams, or they're extended Dynkin diagrams. So this is dm+4 tilde. This is E8. This is E7, and this is E6. So you can kind of just look these up on Wikipedia. These are extended Dynkin diagrams. And maybe I should say a word where you get this classification, or why you might expect these Dynkin diagrams to come up. So the idea is to, first you have to classify the possible singularities that appear on genus 1 curves. You know that whatever these singular fibers are, they have to have arithmetic genus 1. So that's why you can have things like a cusp, or these tack node, or these 3 things meeting at a point. But then for all the other ones, where you have to have these nodal crossings, these transverse, just two branches meeting transversely, you use the fact that the intersection pairing on this collection of fibers has to be negative definite by the Hodge index theorem, and you use that it's minimal to see that all the components have self-intersection -2, and then you look at some linear algebra classification of negative definite forms, and you'll see that they all split up as direct sums of things indexed by these Dynkin diagrams. So that's roughly why the Dynkin diagrams appear, and how you might begin to try to prove this type of classification. But let me give an example of what this fiber actually looks like from the Dynkin diagram. So a Dynkin diagram D4, say, looks like this. But then I put this tilde on top as this extended Dynkin diagram, which means you add an extra vertex, and in this case, the extra vertex goes here. So this is this D4 tilde, and this is supposed to be the graph that gives you the components of your fiber and how they intersect. So in this case, we're going to have 5 components. There's going to be 1 component that intersects each of the other ones. And let me keep this distinguished component in purple. And let's label them. So we'll have this purple component that I'll call A. And then we'll have this component in the middle I'll call E. And then we'll have these other components, D1, D2, D3. All of these are P1s with self-intersection -2. For all these components, but now they also have some multiplicity, and the multiplicity is determined by the shape of this diagram and the fact that the full fiber times any component has to be 0, because it's the fiber of a map. So if I take the fiber and multiply it by any component of the fiber, I have to get 0. And what's special about this purple component is that that always comes with multiplicity 1. So kind of this extra vertex in the Dynkin diagram always comes with multiplicity 1. And so our fiber is always going to be A plus some multiple times E plus N1 D1 plus N2 D2 plus N3 D3. And then using the fact that any 2 components intersect 1 and the self-intersection is -2, you can solve for what these M and these Ni have to be by the fact that F dot C equals 0 and C squared equals -2 for any component. And in this case, A, D1, D2, and D3 have multiplicity 1, and then E has multiplicity 2. And so we can label our diagram with these multiplicities, but again, these multiplicities are uniquely determined by like the intersection form and the property that the fiber times any component is 0. But in this case, we have multiplicities 1, 1, 1, 1, and 2. And so that Dynkin diagram with a special vertex and labeled by multiplicities gives you the information of the fiber. And so you can do the same thing to write down the fibers in all these other cases. And then there's a different type of fiber. So note here, in each of these cases, I said there's always a special component with multiplicity 1. So even though this fiber is non-reduced, it has some components with higher multiplicities. There's always one component that's actually reduced. So the whole thing is not a multiple of a smaller fiber. But there can also be fibers where the whole fiber is some multiplicity times its underlying reduced fiber, or times some smaller, a priori just some smaller divisor. So these are called multiple fibers. And again, maybe this is one of the harder steps in this classification of fibers. You have to classify these multiple fibers, and it turns out these are always of the form MIN, meaning that the reduced fiber is always just one of these I-type fibers, where it's either smooth or a single nodal cubic or a loop of P1s, and then the whole fiber just has some uniform multiplicity, M. Okay, so that you need to work a little harder to actually prove that these are the only multiple fibers, but there you go. And this gives us a classification of all the possible singular fibers for this elliptic fibration. Are there any questions? Oh, and here I should say n is at least 0 and m is at least 2. Otherwise, we're just in this previous case that we already classified. Are there any questions about the singular fibers? And we secretly saw these multiple fibers appear when I used the canonical bundle formula at some point a few classes ago. So I want to maybe make more explicit now the canonical bundle formula, now that we see all the possible fibers. Also due to Kodaira. So let's say that alpha is an elliptic fibration, where again, this means connected fibers that are genus 1 and C is a smooth curve. And everything's proper. And also we want relatively minimal. So of course, in our classification, we had relatively minimal because everything was just minimal. So here relatively minimal means there are no -1 curves in the fibers. So that was an assumption in this classification, because if I start with one of these and I just blow up somewhere, then I'll get a different looking fiber, but it won't be a minimal surface anymore. So here we're already assuming that everything was minimal. Okay, then, and suppose that this alpha has multiple fibers. That we'll list out. Maybe it has M1, F1, ... through MK, FK. So these are all the list of fibers that are in this last category, where the full fiber is some multiple of an IN. Then the canonical bundle of X is given by the following formula. We pull back the canonical bundle on C tensor with this Hodge bundle that we saw already in the proof a few times, and then twisted by a contribution from these multiple fibers. Where the contribution is exactly mi minus 1, where mi is the multiplicity. Okay. And we can write this a different way. So if we write it in terms of divisors, we'll say the canonical divisor as a Q divisor now, because I'm going to use some fractional coefficients, is equal to the pullback of the canonical divisor of the curve plus some divisor L, which is just some divisor that gives you the line bundle R1 alpha lower star OX. Plus a divisor B, where B is of the form sum of mi minus 1 over mi fi, or pi, I guess, where these are the points where fi is the fiber over pi. So basically, here, all I did was say that m minus 1 times our multiple fiber isn't pulled back, because m times our multiple fiber is pulled back. But if I divide everything by m, then as a Q divisor, that's pulled back, because the point f is pullback of p divided by m. So I've just put in this dividing by m inside of my Q divisor. And maybe the last important point is that the degree of this R1 alpha lower star OX dual is the Euler characteristic of OX. Let me just make sure I have that right. Yeah. Okay, so since there's not much time left today, I will sketch a proof of this, assuming the classification of singular fibers. But I want to say a few things about why you want this type of formula. So part of our classification involves classifying these K-trivial varieties. Now we know that we've run this minimal model program. We found a minimal model that is a fibration with K-trivial fibers over some base. So to classify those, we need to classify the possible fibers, and that's what we did above. But we also need to classify the possible base of our K-trivial fibration. And what this tells us is that what this tells us is that the base of our fibration isn't just a curve, but it comes equipped with some extra data. The extra data of these two divisors, L and B. So it tells us that the base of our K-trivial fibration is not just a curve, but is actually a pair of a curve C and this divisor of the form L plus B. And to make this more precise, we know that this C is the proj of the pluricanonical sections on X. So we know that C but now from this canonical bundle formula, we see that the C is also the same as the proj of the sections of not the canonical of C, but of KC plus L plus B. And in fact, these rings are the same. These are the sections, the pluricanonical sections on X are the same as these plurilog canonical sections, these sections of K plus L plus B. So somehow what this is saying is like the geometry of X or its pluricanonical sections is encoded not in the geometry of C, but in the geometry of C with this ring of sections of KC plus L plus B. And so if we want to understand K-trivial fibrations, we need to understand the analog. If we want to understand the base of K-trivial fibrations, this canonical bundle formula is telling us that we need the analog of all this analysis of this minimal model program for pairs, where we have not just a single variety, but a variety equipped with a divisor. So it's our first kind of motivation where we need to study pairs, even if all we care about are varieties in dimension n, if we want to classify those, we actually need to classify pairs in dimension lower than n because of this canonical bundle formula. The other comment I wanted to make is that this L and this B play two different roles. So this is comment 1. Comment 2 is that L measures the variation of alpha, meaning that at least intuitively, we have this alpha, which is this k-trivial fibration. We get some mapped, some moduli space of k-trivial varieties, in this case, the moduli space of elliptic curves. And this L exactly measures like the degree of that map. And this came up very explicitly when we were proving non-vanishing, where we actually saw that this L was like this Hodge bundle, this R1 alpha lower star OX dual was the same as this alpha lower star omega X. And we actually used the moduli space to understand this push forward. And so this is something you should expect in general, that when you have these canonical bundle formulas, you have this piece L that measures like the Hodge theory of how the Hodge theory is varying on your fibers. And then you have this piece B, which measures singularities. It's measuring these extra singular fibers, these multiple fibers. And that's another feature that these formulas have in higher dimensions as well. Okay, so I'll stop there for today.